Hello everyone. In this video I am going to discuss how to solve the problems from laterally supported beams. So the very first step will be determining the factored load. So how we are going to determine the factored load? So the factored load will be, so let's say this is WU. So this WU will be 1.5 times of W walking load. So walking load into 1.5 will give me this factored load. After calculating this factored load, then we will calculate the maximum bending and maximum shear force that is occurring at any section. So if the loading that is acting, it is of UDL, so then the maximum moment and shear force, maximum shear force, it will be WL square by 8, which will occur at the center obviously. So WL square by 8, and the shear force, maximum shear force, it will occur at the support, it will be WL by 2. But if question tells you that the loading is just a point load, if the loading is point load, let's say of value P, and this is my L, in fact this is L effective length. I will discuss what is effective length, and this is also effective length. Here also it is effective, and this is also effective. So in this case, the maximum moment will be WL by 4. So this will be maximum moment, and maximum shear force will be W by 2. My bad. Let's say this is W, okay, not P but W. So this will be W by 2. So this is V max. And the question, if it gives the combination, then we can determine the maximum values of shear force and bending moment also. And what is this L effective? So L effective can be defined as clear span plus bearing thickness. So what is bearing? So your beam will rest on this like masonry or any other structure. So bearing is, this is the bearing. Now the part over which your beam is resting, okay, so this is your bearing. Usually it is masonry wall, so we keep it 230 mm. So the center to center, like from this to this, it is known as effective. So this is L effective. So after finding the maximum moment and maximum shear force, then we will determine the required plastic section modulus, that is ZP required. And this ZP required is basically maximum moment times of gamma m naught divided by this Fy. And this maximum moment we already calculated in step 2. Gamma m naught, we know it is partial factor of safety, that is 1.1, and Fy is like 250, okay, 250 MPa. After finding this like ZP required, what is the required plastic modulus, then what we will do, we will go to table 46. So we will go to table 46 of IS code, like IS 800. So in IS 800, if we go to table 46, then we will get the plastic properties of the beams. So ignore this page 70. This page 70 is basically for my students at Lumbini Engineering College, because we have one code book and it is like made from combination of timber, steel and other. So the page number is shuffled there. So this is for lake only, but for other students, like for global audience, it is like IS 800 table 46. So in IS 800 table 46, the section properties are given. From there, what we can do, we can select any suitable section and we can continue with the design. After selecting the suitable section, then the next step will be classifying the section. For classification, we will be using table 2 from IS code, like IS 800. And if we look table 2, here it is like limiting width to thickness ratio. So for I section, we are mainly focused for I section now. So this is like outstanding element of flange. For flange, we will look this value, like I have highlighted already. So usually we are dealing with the rolled sections. So B by TF. So B by TF, here the value is B over TF. This B is BF over 2. Okay, this B is BF over 2 and divided by TF. The whole formula should be something like this. So B is BF by 2. Okay, so if this is less than 9.4 epsilon, so what is this E? E is basically root over 250 over Fy, and this will be equal to 1 if Fy is 250. So if B by TF is less than 9.4, then the section is plastic. If it is like in the range like less than 10.5, then it will be compact, and 15.7 will give us semi compact. And for the I, like for the wave, and if the neutral axis is mid depth, then these are the values like D divided by TW. We will check this ratio. And what is this D? So this D can be estimated as H, that is height total, just minus 2 times of TF or minus 2 times of R1. So you can keep or ignore this. It will not create that much of difference. But for now, let's keep it. So H minus 2 TF minus 2 R1. And after that, if this is less than 84 E, that is E is 184, then it is plastic. Less than 105, then it is compact, and 126 it is semi-compact. After classifying the section, then what we will be doing is, so after the section classification has been done, then we will check what is the shear strength of our beam. So shear strength, for shear strength we will determine like this VD, and that is defined as Fy over root 3 gamma m naught into shear area. And in I section, mostly the shear is taken by this wave, so we will take the area of this wave, and area of this wave will be H into GW. So this strength, like shear strength, is Fy divided by root 3 gamma m naught times of shear area. And if this value, like this value is greater than V max, then it is safe in shear also. And after that, we will check whether this like I section is in low shear or high shear. So for low shear, if the Vmax is less than 0.6 times of Vd, then it is low shear. And if it is greater than or less than or equal to, and here it is greater than 0.6 Vd, then it is in the high shear. For the low shear, like the design moment Md will be calculated as like this beta into Zp Fy divided by gamma m naught. And for plastic section, this beta will be equal to 1. Okay, for plastic, this beta will be equal to 1. And this strength should be always less than or equal to, so 1.2, if it is simply supported, then 1.2 Zefy by gamma m naught. So this Ze is nothing but Zxx, and this is ZPX, okay, and this is Fy gamma m not well understood. So between these two values, so between like beta b ZP Fy by gamma m naught and alpha ZE Fy by gamma m naught, whichever value is smaller, we will check, like we will select that value as MD, okay. And in the case of high shear, so if the section is plastic, then we will use this formula, so that MdV equal to MD, okay, Mg minus beta into MD minus MFD, and it should be less than 1.2 ZeFy by gamma. And if the section is semi-compact, then MdV is calculated at ZEX times of Fy divided by gamma m naught. So we will discuss these terms in detail when we will solve the numericals. So let's see what is the next check. For the next check, we will look like deflection, and if the loading is UDL, then the actual deflection that is going to occur will be 5 divided by 384 E IXX, and here WL to the power 4, and this W is working load, okay. This is working load, unfactored load, and the permissible deflection will be taken from table 6. From table 6, you can take it as L by 240 if like the support is resting on brittle masonry. For buckling, for web buckling, so web buckling occurs when the material of the web is extremely like weak, then entire like this web will buckle from its original position, and we will check in like this region only. So web buckling, we will check for the support condition. So for the support condition, we assume buckling occurs at 45 degree, and this occurs at the slope of 1 is to 2.5. And let's say if this is the bearing width, and then this value will be B1 plus N1. Now what is N1? N1 is nothing but H by 2. N1 is H by 2. And B1 is the bearing, N1 is H by 2, TW is the thickness of web, FCD. This FCD is calculated from table 9C. It is basically design compressive stress. So FCD is calculated from table 9C. For determining like FCD, we need these parameters lambda and Fy. So Fy, we know that it is 250, and lambda is calculated using this. Here 2.5, D is nothing but H minus 2 times of thickness of flange divided by thickness of web. Okay, after that we can calculate this value. Now it like from table 9C, we will calculate the slenderness ratio, and for the slenderness ratio and Fy, we can calculate the value of FCD. We already did that in compression member. So web crippling check. So for web crippling also, like we will do this like B1 plus N2 into thickness of web into Fy by gamma m naught, and this N2 is defined as so 2.5 times of thickness of flange plus R1. This is thickness of flange, this is radius of root, both will be given, and 2.5, you can see that the slope is 2.5, so it is coming like that. So we can calculate this value, and these two values should be basically less than that VD. This should be less than this VD. So it should be less than strength, design strength, and then we can say that it is safe. So this is how we do for laterally supported beams. I hope this video was helpful from theoretical perspective. In the coming video, I will be discussing some numericals to help you more with the concepts. Thank you for watching.